bit lower than the other quizzes. And it did look like that some of you ran out of time for the problems. But I also feel that quite a few of you ended up writing a lot of the matrices and the steps that were not really needed. For example, if the element for the first problem is horizontal, you don't really need to do a transformation by multiplying it with identity matrices and so on. But anyway, I'll talk about those in a little bit here. So first problem, of course, this was a single truss element, local element stiffness matrix that we've learned. Force vector, where I've actually, all you need to do is to have the 20 kilonewton or 20 kip force here on the fourth degree of freedom. The others for now would be zero, but after solution would be, there would be the reactions. The transformation matrix that was needed was for degrees of freedom 3 and 4 to 3 double prime, 4 double prime, which, as we saw in the examples in the class, was just to modify these degrees of freedom. The good thing was that all you needed to solve this problem was the third three double prime degree of freedom. All the other degrees of freedom were zero. So as long as you calculated the K33 correctly, which happened to be cosine square, you should have gotten the correct answer. But anyway, I was looking mainly for correctness in concept and not really checking the numbers too carefully. So what I wanted to see was whether you knew how to transform the system and impose the correct boundary conditions. So even if your answer was a little bit off, you probably got full points on that. Any questions on this one? Okay. Let's see. And the second problem, I asked you for the element stiffness matrix for this vertical element in both the local and the global coordinates. So local coordinates, no surprise, it's exactly the same that we had for problem 1. The problem is how you transform those local coordinate system to the global coordinate system, which you can actually do just by comparing the degrees of freedom, or you can actually explicitly set up the transformation matrix, which looks like this. Zeros on the diagonal, 1 and -1 on the off diagonals. But if you go the transformation route, it does involve a fair bit of calculation, which if you saw in the homeworks for any vertical element, I pointed out, I think in the lectures also, that is the same stiffness matrix, except now instead of these 1, -1, -1, 1 being in these positions, they are now at the 2, 4 positions instead of 1, 3 positions. So once you knew that, all you needed to do was to assemble those matrices, and at this point there might have been some calculations needed. But again, you only needed to solve the middle 2 cross 2 of this matrix, upon which you should have gotten the solution 1.9 millimeters and 0.45 millimeters. So once again, I was looking at the concept of the concepts and the steps that you followed here. I think some of you still made the mistake about assembling the local element stiffness matrix here, not really the global. You should assemble the global stiffness matrix, not the local stiffness matrix. And finally, this problem was the method of joints problem, where I think if you just follow along the examples that we did in class, you should have been able to set up a system that looked like this. And the hint said that if you start solving from the first row, you don't really have to solve this big 6 cross 6 system by hand. If you start solving from the first row, you can go down that way, one row at a time, and you'll get the solution. It's just one line statements really. And the 2-story and the n-story problems were really just extensions of the same format. So if you look at these coefficients, they just keep repeating over and over for 2-story and n-story problems. And actually, even just by looking at this picture, you should be able to see that the 4 kilonewton force would go into the horizontal bar for all of these elements, and the 3 kilonewton force would go into the vertical element and keep on getting added together to reach the final answer. final compression force at the bottom. So I think, as I said, overall look like uh, if you did a lot of steps for the matrices, writing matrices takes time. So you've got to be very efficient with the stiffness method. But I'll post this solution up, and if you have any questions, let me know. And of course, please do check the totals on your paper right now. And if you find any discrepancy, let me know immediately. So, anybody have any questions on the quiz? No? Go ahead. You mean the average, I think, is 10.5. Usually it is around 11. So it's not a big fall, but it's a little bit lower, yes. Which is still 70%. So it's not all that bad. But I think, and another point I should mention, of course, and I think I've mentioned this previously when I distributed the quizzes, that I will indeed drop the lowest quiz score that you have. So it's the best 3 out of 4 that we'll take. And if you missed a quiz, that indeed means you'll get only 3 of those. Go ahead.
Go back to part D of problem 3.
Part D of problem 3. So it says the horizontal components are all 4K compressive, and the odd numbered elements just keep on adding 3 kips, 6 kip, 9 kip, and so on. 3i kips would be compressive. Okay, so let me turn the stage over to Dr. Liu, who will give you an introduction to SAP. And I think you wanted to pull up your slides, right? Let's see. Oh, this one? Okay. It's all yours.
Okay, everyone. So for today and the lecture on Wednesday, I'm going to talk about using SAP 2000 to do some structural analysis and designs. I think some of you have already been using SAP 2000. It's a very powerful structural analysis and design software that allows you to do a lot of structural analysis and designs. It has a lot of powerful tools, including some 3D graphical modeling environments, and it has a lot of built-in templates and design codes that are ready for you to use. And also it has some advanced analytical techniques like large deformation, material nonlinearity, and dynamic analysis. If maybe not all of you have have been doing such advanced analysis of structures, but if you have interest, you can definitely look into it and try to use SAP to solve. So on their official website, there are many useful informations that you can look at, such as you can go to the features, and there are the introductions on the interface, modeling templates. There are not just like 2D templates. There also have some 3D geometries for solid structures like dams, and there are also some. You can also analyze the data in terms of the table format, which is also very useful. And the meshing tool, this is really a finite element software, so there's meshing, structural components, frames. There are a bunch of them. You can look at them, and there's also some. There's also this watch and learn tab, which comprises of lot of useful tutorials. Yeah, so it has static dynamic analysis and also section designs and nonlinear analysis. And these are very useful tutorials that you can go through. So, so today I'm gonna cover two examples that you may be interested in. First would be the trust analysis. You have already done a lot of practices on this. And then secondly, I will also talk about a design analysis and design on a 2D frame structure. So first, let's look at this truss analysis. This is the indeterminate truss with some members are steel and some are in aluminum material, and they have all various cross sections and subjected to multiple point loads. So instead, this is the user interface. So we can start with a new one, and the unit here is in kips and inch. So we choose that, and so we say new model. Okay, it's like taking some. Okay. So here you can use some templates such as the 2D truss, but it only have three types of truss that you can use. Since we have a geometry that is not any of these three, no. So you can start with a grid line so that you can draw by yourself. So here, first we define how many number of grid lines. So there are 4 in this direction, and in z direction there will be just 2. And also we know the dimension in the z direction is 216. So here we define as 16. And okay. So now we have the grid lines. Since it's a 2D problem, so we're really looking at the x and z direction only, so we can change the view into the xz direction. And then before we start drawing the members, we can first define the materials and the cross sections. Okay, so here let's first define the material property. Since we have both steel and aluminum, so first we define the steel property, and the rest of it are just as we need it. So you can modify the name to whatever you want. So here I'm just saying steel, and then add a new material. Here, okay. Here I can define aluminum material. Okay, and here to modify and show the materials, you can see the Young's modulus and everything. Okay, so this is what we need.
Let's see. There might be like some issue, but keep going.
Okay. Okay, now we have both material properties defined. Now we need to define the section properties. And as we know, there also it has to.
Yeah, that should be.
Okay. So we know that there are 3 different sections, so we need to define them one by one. First, we have a steel section. Since it's just a truss problem, the property for sections that we really care about is just the cross-sectional area. So we can define some solid cross-sections, say steel 8 inches square inches. And here we say the material is steel and section designer. Okay, so this is also a very powerful tool that allows you to design any type of cross sections as you want it. For example, here we want to define some rectangular shape, and just click on anywhere. It will draw this cross section for you, and then just right click on it. It will bring up the section properties where you can change the materials and the locations and the geometry properties. So here we're looking for 8 square inch cross section. So we say just say 4 by 2. And now we have this cross section, and we can check the properties. Apparently the cross sectional area is set to 8. And here, since we're just doing a static analysis, we don't want to involve any self-weight or mass, so we can just change those properties to 0. And okay, so now we have one property. And similarly, we have steel 12. Okay, and so we'll say 4 by 3. Wait. Okay, and then the last one would be the aluminum. Aluminum is 16, so we can define as 4 by 4. Okay, just let me double check whether I have, oh, here, yeah, it should be steel. Okay, so now we're ready to draw the members. You can click just on the draw frame cables here. Then it will allow you to draw any sections that you have just defined. Or you can click on none. It will just draw the geometry of the structure first and then allow you to define the sectional properties later on. After you draw it, you can right click. It will leave you in the draw module and then continue from somewhere else. So now the structure is drawn. Now we want to assign the correct cross-sectional properties to those members. So you click on the select mode. Here we have different cross-sections of the member, 2 aluminum and rest will be steel. So you can select those. If you do from left to right to left to select, it will select anything that you touched. But if you are going from left to right, it will only select those are completely included. For example, now it's not selecting, but if I do that, those members will be selected. Okay, so if I clear all selection and 12, okay. I'll select those and then assign frame from section to assign the steel 12 to them, and these 2 would be aluminum. Assign aluminum, and the rest would be the steel 8. Okay. Okay. So now the members are defined. Now the next we can define the boundary conditions. So we know that there is a pin and 2 rollers. So we can go to, first we select this point and then go to assign joint, joint restraints, and select the pin here. So there's a pin. And then select these 2 joints. We'll assign the restraint with the roller. And now we can see that there are rollers assigned to them. And another thing is, since we're doing trust analysis, right now the members we created are frame members. So we need to release the moment, the rotational degree of freedom. So the way we do it is that we select all the members. Okay. And then,
Do you have duplicate members there?
no. What?
That's okay.
Okay. Fine. Wait. Stopping joint. Okay. Okay. So here is this release or partial flexibility. Here you want to release the moment in the major axis. So here just click those 2 to start and end to be 0. And now it displays that all the members at the joints are released. So now your frame member becomes trust members. So now boundary conditions and members are defined. We want to define some loadings. So we have 3 point loads at these 3 locations. So first one here, we'll assign joint loads. First, it's in the z directions. It will be -75, and check the units are correct. Okay, and then select this one, assign joint loads. It will be 0 and 25. And -60. Okay, now so everything are set correctly. Now we can start to run this problem. So if you go to analysis, click on run, or you can just simply click on this button here. You can see that there are multiple cases that you can run. You can run a linear static on the dead load, or you can also run a model analysis, which is actually a dynamic analysis. But we don't want to run this one now, so we can just select it and say run or do not run case. It will show that it will not run. So it will run only the first linear static case, and if you just click on run now, then now the program will run. Okay. So this is the deformed configuration, but it's actually not right because the cubic curve is selected. It means that it will fit the deflected shape with some cubic function. So you just uncheck that. It should give you the right deflected shape. Okay. So now you can also check the wire shadow, which gives you the original configuration as well, and right click on any okay, yeah, so you just put your mouse to any joint. It will give you the displacement and reactions at those joints, and also you can display the actual force within the members, and just place your mouse there you can see the values, and also we want to check whether it is correctly say the share. I guess maybe these two are not released. Yeah, there shouldn't be any. There shouldn't be any share, but I guess I can just. I just open my previously Dropbox.
Up there. Up. Okay. Yep.
Just thinking. Oh no, it's once it's run, it's done. So now it shows that share is 0 for all the members, and let's check the moment as well. And moment is also 0 for all members. So that's about everything for trust analysis. Do you have any questions now? We can discuss.